So yeah, so that's differentiation. So you remember with differentiation, it's fairly straightforward, okay? There's only a few things that you need to know, okay? So let's just create a list of the things which we need to know for differentiation. So some people ask for sort of a summary. Here it is. Remember, all of this is in the lecture notes anyway, okay? So what's the first thing that we did with differentiation?
Gradient.
Yeah, good. The idea that differentiation is the gradient or the rate of change. Okay, so that's a really fundamental idea, okay? And of course we wrote that as dy by dx, or we could write the function prime of x, or just simply y prime, okay? So 3 ways to write differentiation. Okay, what did we look at next? So what type of functions did we differentiate first?
Polynomials.
Good, yeah, we looked at polynomial functions differentiated first. Looks at polynomial functions, okay? So in other words, functions of the type x to the power of something, okay? And we knew that the derivative, just remind me, what's the derivative?
M minus 1 multiplied with x over... oh, sorry.
Yeah, bring the power down, reduce the power by 1, okay? That's a simple rule. Okay, then what type of functions did we or what did we do next? Stationary points, right? So just remind me, what were stationary points?
So rate of change is 0.
Perfect. The rate of change was 0. Okay, is equal to 0. And then from there, we looked at the type of stationary points. Okay. So remind me, a maximum. How do we work out a maximum?
The second derivative is less than x.
Exactly. So it's a decreasing function around that point. Okay. So for a local maximum, the second derivative, in other words, the rate of change of the gradient, the rate of change, is got to be negative. It's got to be decreasing. If it was a point of inflection, how do we find that?
Less than greater.
Not quite. As if it was equal to 0. So it goes from increasing then to decreasing, or vice versa. If we were looking at minimum, how do we do that?
It's greater than 0.
Absolutely. So dy by dx squared has got to be increasing. It's got to be greater than 0. Okay? Good. Then what did we look at? So we've done with polynomial functions. We looked at finding stationary points. Then what do we look at? Well, okay, tangents kind of buried in here. So we looked at finding the equation of tangents and normals and stuff like that. Okay. What do we look at next? So we've done polynomial functions. What type of functions did we look at differentiating next? Good, trigonometric functions. Okay, and we came up with this table that the derivative of sine was cosine. The derivative of cosine was negative sine. The derivative of negative sine was, and derivative of negative cos?
Sine.
Back to sine again, yeah? Then what did we look at?
Chain.
Perfect. Then we looked at the chain rule. Actually, before we looked at the chain rule, what type of functions did we look at next?
Logarithmic.
Yeah, exponentials and logs. Exponentials and log functions. Okay, so in other words, if I want to differentiate e to the power of x, what's that equal to? Good, and if I want to differentiate the log of x, natural log of x? Anybody remember what the derivative of the natural log of x is?
1 over
Perfect. Well done, okay. Then we looked at the chain rule, okay, which you remember, is just the Altieri rule. Okay, then what did we look at? Perfect, the product rule. Then what's the last thing we looked at, last lesson? Quotient rule, right? So remember, the product rule, if you wanted to differentiate a product of two functions, what was that equal to?
you multiply v dash plus u dash b.
Perfect, okay. Can anybody remember what's the derivative, so the quotient rule, what's the derivative of the quotient of two functions? Did anybody write it down?
I can write it down. I cannot say it.
Yep. U dash.
Yeah, yeah, yeah.
Minus UV over.
And V squared.
Good.
Okay.
Excellent. Yeah. We happy with that? Okay. So this is kind of a summary of everything that we looked at in differentiation. Okay. By the way, at the end of last lesson, I gave you a challenge. Okay. I asked you, can you differentiate tan x? Did anybody get it?
Yeah.
Okay. What do we get it out as? Okay, so we could think of this as the derivative of sine x over cos x. Okay. Yeah, because tan x equals sine x over cos x. Then it's just the quotient rule, right? Because it's a derivative of two functions. So, okay, we got v times by u dash. So v is cos x multiplied by the derivative of sine x, which is cos x. So it's cos x times cos x, cos squared x, okay? Minus u multiplied by v dash. So u is sine x, okay, multiplied by the derivative of v. So what's the derivative of cos? Minus sine. So I'm just going to change that to a positive and change that to a squared. So you get a positive time, yeah. Okay, and then on the denominator, okay, I get v squared, which is going to be cos squared x. Okay, what's cos squared plus sine squared? It's just 1, yeah? So I get 1 over cos squared, which if you remember your reciprocal functions, if you get 1 over cos, that's going to be equal to sec squared. Okay, so we don't focus on reciprocal functions too much, but effectively when you have reciprocal cos or reciprocal sine or reciprocal tan, it becomes just sec, cosec, or cot. Okay, so if you're not sure, if you want 1 over sine, that's equal to cosec, okay, of x. And if you want 1 over cos, that's going to be equal to sec. Okay, and if you want 1 over tan, does anybody know? It's going to be cot. Okay, and the way which I remember that is always the third letter. So if you notice, that begins with an S, sine begins with an S, third letter then is cosec. That begins with a C, third letter is sec. Okay, and then that begins with a T, third letter is cot. Okay. Good, fine. So the derivative of tan x is equal to sec squared x. Okay. So that's differentiation. That's differentiation. Okay. Now what we're going to move on to today is this idea of integration. So just by show of hands, who in here has met integration before? Okay. Okay. Okay, good. So we've met differentiation. Now we're going to move on to integration. Now one way that you can think of integration is it's just the reverse process of differentiation. So just like if I said 3 plus 4 equals 7, if I wanted to start at 7 and get back to 3, I would take away 4. I do the reverse operation. So addition and subtraction are reverse operations of each other. Multiplication and division, reverses. Powers and roots, they're inverse of each other. Differentiation and integration are inverses of each other. Is that okay? Right? So let me make some space.